How do we resolve collisions when hashing? You've seen dictionaries, you know what a hash table is, what a hash function is. Now let's resolve collisions, and we're going to see two approaches, with chaining and with open addressing. With chaining is very simple. So why do we need to resolve collisions? We need to resolve collisions when two keys hash to the same cell. How does chaining solve this? Just in a straightforward way, let them both go to that cell. But then we need to store both of them there, and we do so simply by storing all elements or all keys that want to go to the same cell in a linked list. So that might look like this. So here in this example, we have 3 keys that are all hashed to 2. So then in our table, we will have a linked list of those keys. And that's all. Of course, if there's satellite data, we also have to store that. Here we will concentrate on the keys. So now that we know how we want to store the data, we need to make sure that we implement the operations insert, delete, and search. We start with insert. So we have an element X. We take the key, we hash it, it brings us to a cell. We insert the element at the head of that list, and that's it. So how does that look like? We have X, it has a key. The key hashes to some cell I. Here we have I. There's already a linked list here. So we insert that element at the head. How long does that take? Inserting at the head of a linked list takes constant time. So insert we can do in constant time. How about delete? So for delete, we're going to assume that we get X, which in particular means that we can access X in the linked list, so we don't need to search it. Otherwise, we have to first do a search and then delete, so then we additionally get the running time for searching. So here we have a linked list. We assume we have a pointer to that element that we want to delete. Now we simply delete it. We have to be careful here. Is deletion that simple? So can we do it, as I now claim, in constant time? Yes, we can, but we have to be careful that we don't take a single linked list, but a doubly linked list, because with a doubly linked list we can access the previous, and with that easily delete the element X. So we have insert and delete in constant time. Now we need to search. Searching again is straightforward. We take the key, we go to the corresponding table entry, let's say that's I again, and then we search through the list until we find the element. So let's assume that element is not actually in the table. Then the running time for this will be of order length of this list. Otherwise, if it is in the table, so in this setting, if it's maybe K4 or K6, then it's one order of 1 plus the number of elements that I search before I reach that specific element. So that's the running time here. And of course, if we're unlucky, every key is hashed to the same cell. So we might have a linear number of keys in one cell, and then the worst case is linear. So the worst case running time for searching in a hash table is linear. That's bad news. But the good news is that this is not the behavior that we expect. So what we expect is much closer to the average case. Let's analyze the average case running time for searching. For that, we need to have some assumption about the distribution, and what we're going to assume is a simple uniform hashing assumption. And what that means is that any given element is equally likely to be hashed into any of the m slots. So what does that mean? It means in particular that if I take all the keys from the universe and place them in a hash table, those would be uniformly distributed over the hash table. Also, the key that I'm searching for has the same probability of being in any of the cells. Of course, as soon as I have the key, it will correspond to a specific cell, but I can assume that when I get a key, that the probability that it is in any of the cells is equal. And the analysis will use the load factor. So what is the load factor of a hash table? That is simply how full it is. And that is number of elements divided by table size. So a load factor of 1 means that on average I have 1 element per cell. A load factor of 1/2 would be roughly an element per every second cell. I could also have a load factor of 2 because we store things in a linked list, so we can have several elements per cell. That's a load factor. N divided by M. Number of elements divided by table size. So let's do the analysis. And what I claim is that if we have the simple uniform hashing assumption, then an unsuccessful search takes order of 1 plus load factor time. So we have all of these running times with 1 plus. What does that mean? It means that any operation that I'm doing here will at least take constant time. Then the interesting part will be actually the alpha factor. So the alpha factor, if the load factor is high, could be very high. Typically, if I make sure that overall the number of elements is only a constant factor larger than the table size, then also this will be constant. So let's prove this. We are searching for an element, and the expected search time corresponds to the expected length of the corresponding list. Now, the element that we're searching for, because of the simple uniform hashing assumption, it has the same probability of being in any of the lists. That means that the expected length of a list actually corresponds to the average length of a list. So what is the average length of a list? For that, I simply have to count all elements together and divide by the number of cells. So that is N divided by M, but that exactly is alpha, or load factor. And that proves the theorem. So, and again, I didn't mention the 1 here, but the 1 is simply that searching will at least take constant time. Let's have a quiz. This is part of an exercise from the practice notebook, which is also linked. So you can also do the full exercise. Also, to solve the quiz, you will want to simply solve part of the exercise. So this quiz will take a moment. And the question is, so we have a hash table, we have a hash function, we have some numbers that we want to hash into that table. The question is, how long is the longest linked list if we hash those 5 numbers? The correct answer is 3, C. So, and that is 8, 40, and 88. All of those go into cell number 9. Let me just demonstrate that for, let's say, 8 and 40. So 3 times 8 plus 1, that's 24 plus 1, that is 25. Modulo 16 is 9, because 16 plus 9 is 25. 40, 3 times 40 plus 1, that is 121. Now, 16 times 7 is 70 plus 42 is 112. So 112 is divisible by 16. 112 plus 9 is 121. So also 121 mod 16 is 9. And now you can do the same for 88. So much about chaining. So what have we seen? Chaining simply puts everything that hashes to a specific cell into a linked list for that cell. Insertion takes constant time, deletion takes constant time if we have a pointer to the element. Searching in the worst case takes linear time, but if we have the simple uniform hashing assumption, it actually takes an expectation constant time, assuming that the load factor is constant. Now let's see a second method for resolving collisions, and that is open addressing. So we want to resolve collisions, and we've seen how to do it with chaining, but chaining has these linked lists. And linked lists somewhat take away the beauty of the arrays, which very compactly store data. And for open addressing, we want to avoid this. But then, if we have an element that hashes to a cell that is already taken, then I need to find a different spot for that. And for that, I probe the hash table until I find a free spot. And this probing we have to do in a clever way, because obviously, if I place an element somewhere, I will also have to at some point find it again. Let's first do this by example. So here we have a hash table of size 7. As hash function, we take division method, h of k being k mod 7. Let's insert some numbers. Let's insert a 3, hashes to cell number 3. Let's insert 18. 18 mod 7 is 4, so it goes to cell 4. Inserting 28. 28 is divisible by 7, so that goes to cell 0. We want to insert 17. So 17 mod 7, so 14 plus 3, goes to cell 3. Cell 3 is already taken. Now we want to have a clever way of placing the 17 into the table anyway. So a simple solution here would be simply to say, let's look at the next cell and see whether we can place it there. The next cell is taken, but the cell after that, there's place, and there we place the 17. In this way, we avoid the extra storage that the linked list would need. We do have to be careful because now the table can actually fill up. So at the point where we have, let's say, m elements in the table, then we're really in trouble. Probably already before that, because even the mth element will have a very difficult time finding a cell. So the load factor will have to be smaller equal 1, and it would be better if it's not too close to 1. So if a cell is taken, how do we decide which cell to probe next? So there are different schemes for that, different variations of open addressing depending on the strategy. Generally speaking, our hash function is now a function of 2 arguments. We have the key k, but we also have I, the number of probes that we already did. So we will be probing a probe sequence starting with hk0, that is simply what we try first. But then if that's not successful, we will try hk1 and so on. And depending on the variant, these probe sequences will be defined differently. So if you think of the example that we previously saw, there, for hk0, we were simply trying some hash function. It was k mod 7. But then if that one was taken, we would try the next cell. Next cell being here plus 1 for is1, plus 2 for is2. So this is the probe sequence that we would have been trying there, obviously making sure that we stay within the table by doing modulo 7. So this is just an example. We will see that in a moment again. I'm just giving it here to make this a bit more concrete. So you can think about general probe sequences, but if you want to have something concrete, you can also simply think about this hash function. Whatever your probe sequence is, it better be a permutation of the numbers between 0 and m minus 1, because that means that eventually you will probe all the cells. So if it's not a permutation, it means that the table might not yet be full, but you're not trying everything, so you cannot place an element. Of course, when the table is full, this also won't help you because then the table is full. Now we want to implement insert, delete, and search because those are the dictionary operations. Let's start with insert. And here's pseudocode for insert. So we start with I is 0. So that is how often have we already probed, 0 times. And then as long as I doesn't reach m, and if it reaches m, then the table is actually full, so we could have seen that coming. And while at that position there's not none, meaning there is already a number, then I increase I. So I simply increase I until I find a none. Now if at that point I is smaller than m, so meaning if the table isn't full yet, we can simply place a key there. Otherwise, if the table is full, we should throw an exception that the table is full. Now keep in mind, we're actually inserting an element x with a key k, but here we always simply think of the keys. Now let's do this by the example of linear probing, and linear probing is simply the hash function that I already showed you. So we have a table of size m, we have an ordinary hash function h prime of k, and now we're going to do h prime of k plus I. So first we try h prime of k, then we try h prime of k plus 1 plus 2 plus 3 until we find a free spot. Always doing modulo m so that if we reach m, we restart at 0. So now the example, this is our current hash table. We want to insert the 17. So that's the example that we already saw. We will first have I is 0, so meaning we try h prime of k. While this is not none, 3 is not none, we increase I by 1, we go here. We increase I by 1, we go here. And now we have a none. We haven't reached m yet, so we can insert the key there. So let's search. And searching follows the same principle as inserting. So we start with I is 0, so we hope that the key is where it should be. So we're going to check first HK0 and check whether we see the key there. If we do so, we are going to report it. Otherwise, we're going to increase I by 1, check again, increase I by 1, check again, and so on. We can stop as soon as we've seen a none, because if we see a none, we know that the key cannot be in the table, because otherwise the key would have been there. Also, we can stop if we ran through the whole probe sequence, because then we ran through the whole table without seeing the element. In that case, we can simply report that the element is not there. Let's again do an example with linear probing. So here's my hash table. Let's say I'm now searching for the 17. So 17 should hash here. So we're going to check that spot. There is an element there, so it is not none, but it is not the element that I'm looking for. So I simply increase I by 1 and continue. Again, there's an element, it's not the one I'm looking for. I increase I by 1. The 17 is there, yay! I'm going to report that I found the 17. Let's say we now search for the 25. 25 mod 7 is, so we have 21 plus 4, that will be slot 4. We see an 18. 18 is not 25. We increase I by 1. We see a 17. 17 is also not 25. We increase I by 1. Now we have a table say with a none. And at this point we can say 25 is not in the table. Deletion. So with deletions we have to be careful, because if you think about how we did the search, we searched until we found a none. Now imagine we deleted an element, then suddenly there could be a none where previously there was a number. Now search fails, although maybe the search should have continued. So to avoid this issue, delete works as follows. We simply remove the key from the corresponding slot, but not write none into that slot, but write in a special symbol into that slot, deleted. So here, for instance, we delete 18 by simply putting del in there. So again, either we already have a pointer to the 18, otherwise we would first search for the 18 and then delete it. In any way, we have this special value. And now what we need to make sure is that if we search, so if I, for instance, now search for the 17, then I have to, if I see a del, continue. On the other hand, when we insert, we should treat the deleted value as an empty cell where we can insert, because we can simply use it. Now, there is a drawback, and the drawback is that the search time will be no longer only depending on the load factor. So imagine you first insert lots of elements and then you delete again lots of elements. It might mean that you have lots of these del special values in there. So it might mean that your search takes very long, although there's basically no elements in your list. So that's something to take care of. So if you need to delete a lot, chaining might be the better option. Alternatively, you could do something where at some point you clean up your table. But if you want to keep things simple, if there's lots of deletions, simply use chaining. Now let's talk about probe sequences. So what are suitable probe sequences? We are going to have an ordinary hash function, h prime of k, and there we can simply use hash functions as you would use them also for chaining. Now there are different ways of generating probe sequences. The first and simplest one, and the one that we've already seen, is linear probing. so where I simply take a plus I term, meaning I check whatever I get by the ordinary hash function, but if that's taken, I check the next spot, and so on. A problem here is that two keys that hash to the same cell will also have the same probe sequence. So the initial probe determines the whole sequence, and overall there are only m distinct probe sequences. So ideally you would want to have more different probe sequences, because then those probe sequences distribute elements more randomly. But the problem is even worse, namely, as soon as a key tests the same slot as some other sequence, it will follow the same sequence from then on. What that has as a result, that linear probing suffers of something that we call primary clustering, meaning that if you have long runs in your table, those tend to get longer and longer. So if you have a big block taken, then with a sufficiently high probability, a new element will actually hash to that block, and then it will simply make it by one longer, and the next one by one longer, and so on. So that is primary clustering, and that's a problem that you have with linear probing. So the average search time, if you get these clusters, increases. An alternative is quadratic probing. So quadratic probing also uses an ordinary hash function, and then instead of the plus I, it has this linear term, plus I, actually c times I or c1 times I, but then also a quadratic term, c2 times I squared. So now you still have the situation that if this is the same for 2, so if 2 keys hash to the same cell, to the same initial probe, then the probe sequences will be the same. So you still have the problem that the initial probe determines the entire sequence. You still have the problem that you only have overall m sequences, but if you have another element that kind of joins a sequence somewhere in between, it will not follow the same sequence from then on. So we don't have the primary clustering, so we call this secondary clustering, meaning that keys that have the same initial probe result in the same probe sequence. We do need to be very careful to choose C1 and C2 in such a way that we actually get a permutation. So that is a drawback of quadratic probing. You have to, it only works for certain values of C1 and C2 and M. A good alternative is double hashing. So for double hashing, we again have an ordinary hash function, but then we also have a second hash function, here this one, h double prime. And what we now do, it looks very much like linear probing, but instead of plus I, we do plus I times the secondary hash function. As a result, even if two keys go initially to the same slot, they won't have the same probe sequence unless also the secondary hash function is the same. One thing that we need to be careful about is that h prime should be relatively prime to m. So what does that mean? It means that h double prime and m should not share a factor. So for instance, if m is 6 and h double prime is 2, then the probe sequence for k would be h prime of k plus 2, h prime of k plus 4, h prime of k plus 6 mod 6. So again, simply h prime of k. So we would not end up in a permutation if h double prime of k and m share a factor. So now with this, we already have m squared different probe sequences. So previously, for linear probing and quadratic probing, we only had order m probe sequences because the first probe determines the whole sequence. Now I have this combination of h prime, m options for h prime, m options for h double prime, so that gives me m squared probe sequences. Next, we want to analyze open addressing, but let's first have a quiz. And the quiz is about double hashing. So we have this table of size 13. There are already elements in that table. Here's our primary hash function, the secondary hash function. The question is, we insert 23, where does it end up? 23 ends up in slot 0. And why is that the case? So let's try 3 times 23 plus 1, that is 69 plus 1 is 70. So 13, so we have 65 is divisible by 13, so this hashes to 5. 5 is taken. So now we have to take 1 time h double prime. So that's k mod 15, 23 mod 15, that gives me 8. I do 8 plus 5 is 13. Mod 13 places the 23 here. And this is also part of the practice exercises, so you can check the notebook for the full solution. Let's analyze open addressing. Again, we will need to assume some kind of randomness from the hash function. Not only the hash function, but of the probe sequence. So instead of the simple uniform hashing assumption, we now have the uniform hashing assumption, meaning that any of the permutations of 0 to n minus 1 is equally likely as a probe sequence. We also need to assume that the load factor alpha is smaller than 1. And we're going to assume that we haven't had any deletions yet, because as we know, deletions can mess up how long the search time is. And now our claim is that the average number of probes that we need for an unsuccessful search is of order 1 divided by 1 minus a load factor. And for a successful search, it's a bit more complicated, 1 divided by alpha times log 1 divided by 1 minus alpha. The second term we're not going to analyze, we're going to focus on this first term. But let me first say what that means in terms of if the load factor is high, what do we get? So if the table, let's say, is half full, meaning that alpha is 1/2, then we have 1 divided by 1 minus 1/2, so 1 divided by 1/2, that's 2. O of 2, theta of 2, perfectly fine. The closer the load factor is to 1, the closer 1 minus the load factor is to 0. So then 1 divided by that can be very large. So we will want to make sure that the load factor is a constant bounded away from 1. So for instance 1/2 or 3/4. All of that is fine. Let's prove this. So we want to compute the expected number of probes during a search. So we can write down the expectation as a sum over the values of I that the number of probes can take. So that's all I is between 1 and n times the probability that the number of probes actually is this value I. So that's a standard way of computing expectation. We will want to compute expectation slightly different here, and we can rewrite this sum in the following way. We take simply the sum of probabilities that the number of probes is larger equal I. And if you haven't seen this way of writing expectation yet, it is very easy to derive. Just think of these values here. Let's call them Pi. So Pi is the probability that the number of probes is I. Then if you split the sum, so you have 1 times P1, you have 2 times P2, which you can write as P2 plus P2, and you have 3 times P3, which you can write as P3 plus P3 plus P3, P4 plus P4 plus P4 plus P4. And now let's sum this up vertically, you could say. So P1 plus P2 plus P3 plus P4 plus P5 and so on. That is the probability that the number of probes is larger equal 1. And then P2 plus P3 and so on is the number of probability that the number of probes is larger equal 2. And that's exactly the sum that we have here. So now we have this sum. So now we want to compute these values here. So the P larger equal I. So what's P larger equal 1? So a probe sequence always has length at least 1, so the probability of this is 1. What is the probability that the probe sequence has a length 2? So for that, my first probe must fail. What is the probability that it fails? Because of the uniform hashing assumption, it fails with probability n divided by m, because n slots are taken out of m, so the probability that I hit one of them is n divided by n. So the P larger equal 2 is n divided by m, which is the load factor alpha. So how about P larger equal 3? So for P larger equal 3, first my first probe needs to fail. So that has probability n divided by m. Then my second probe also has to fail. So there are n minus 1 slots left and n minus 1 elements that I could hit left. So that is n minus 1 divided by m minus 1. So I get P larger equal 3 is n divided by m times n divided by m minus 1. which I can bound by n divided by m squared, which is alpha squared, so the load factor squared. And more generally, p larger equal I is then simply bounded by alpha to the I minus 1. And that's also the case for p larger equal 1, which I can write as alpha to the 0, and p larger equal 2, which is alpha to the 1. So now I know what these p larger equal I terms are, so the terms that I have in the sum for the expectation. So let's sum them up. So I get the sum p larger equal I. I can now bound this by alpha to the I minus 1. And then let me shift the index by 1. Then I get the sum to the alpha I. And you see now my sum starts at I is 0. So instead of starting at 1 and having I minus 1, I start at 0, I have I, and my sum also only goes up to n minus 1 now. So I have the sum alpha to the I. So this is a geometric series, and we know that it converges to 1 divided by 1 minus alpha, and we can bound this also simply by 1 divided by 1 minus alpha. And that's exactly what we wanted to prove. So now we know that the expected time for an unsuccessful search is of order 1 divided by 1 minus alpha, meaning that if the load factor is, let's say, smaller than 1/2 or smaller than 3/4, this is simply a constant. And likewise, even also for a successful search, so I'm not doing the analysis here, but again, as long as your load factor is bounded away from 1, so let's say 1/2, 3/4, you're perfectly fine. So let me mention one drawback of hash tables. Hash tables are really just good for insert, delete, search. So if you want to do any other kinds of operations like finding the minimum success, that is not easily done in a hash table. Let's have a quiz about that. How much time does it actually take to find the smallest element, so the minimum in a hash table? Constant, O of n, O of m, O of m log m. The correct answer here is O of m. To determine what the minimum is, we have to search through the whole table. So let's sum up what we've seen so far. We've seen hash tables, how to resolve collisions by chaining or open addressing. In the previous video, I talked about what is a good hash function. Now, if you made it this far in the video, let me as an extra show you how hash tables work in Python. So how dictionaries in Python are implemented. So you have the dict or the sets. Again, you don't need to use integers as keys. You can also use strings, and those strings would then by Python be mapped to hash to integers and then used for hashing. And then a set is simply a dictionary where we only have the keys. So before I say how in Python collisions are resolved, let's compare chaining and open addressing a bit more. So let's assume I have a nearly full hash table. So what's better, chaining or open addressing? So in this case, so if the load factor is very high, then chaining is definitely the better choice. Because if it's nearly full, chaining also simply, so if I have a load factor of essentially 1, chaining takes 1 plus load factor, so O of 2, which is constant time, while an unsuccessful search with open addressing in this case is 1 divided by 1 minus the load factor. If the load factor is nearly 1, this will be up to O of m. So here chaining is better. Also, if you have many deletions, what is better, chaining or open addressing? Chaining, because for open addressing, the running time might no longer simply depend on the number of elements in the table, but you might have to go over lots of deleted elements. So what do you expect Python uses? Chaining or open addressing? It uses open addressing. And why does it use open addressing? Chaining has its overhead of the linked lists, which need more storage, which if we can avoid it, we will want to avoid it. The disadvantages that I just mentioned are actually not problematic because they're related to high load factor. But what can I do about a high load factor? I can use dynamic arrays. I can use principles of dynamic arrays and simply rebuild the table if it's too full. So Python will rebuild the table as soon as it's 2/3 full. How do we handle many deletions? Same way. Simply rebuild the table if we have lots of del values. Now finally, how does the hash function or the probe sequence look like? So this is a bit more complicated, but it's interesting to look at. So let's take a closer look. And the implementation that I'm showing to you here is implementation from CPython, but I'm not showing the C code, I'm showing a Python version of this. N is here the size of the table, so not M, but N. Let's take a closer look, and what I'm going to show you here is what happens in CPython, so the standard Python implementation. But I'm not showing the C code, I'm showing equivalent Python code. N is here the size of the table, and H is your hash value. So you're using division method, so first you're trying H modulo N. If that's successful, that's the spot that you take. But from there on, things get more interesting, because now what we do is we're taking 5i plus something that depends on H plus 1. So if you ignore this perturbation term, then you would get a probe sequence. Now there is this permutation term, and that is simply the H shifted by some bits. And the reason this is done is that we make sure that we really use all of the bits of H. But this will go to 0, so eventually we will probe the whole table. And that's what's happening here. So if you have used dictionaries in Python, you will have seen this concept of sorted dictionaries. So how can that make sense? I mean, we were saying dictionaries are hash tables, they're not sorted. So why sorted? It makes a lot of sense, but the sorting is not the hash table is sorted, but your data is sorted. Let me demonstrate this. So classically, if we think of a hash table, we would be thinking of something like this. So here, the keys are also strings, and we have some values, and this is the hash value for that. So we will have tuples of the hash value, the key, the item. And then in the empty slots, we will have also such tuples, but they won't contain anything. Now this can be made more efficient in terms of the space that is used. And that is what sorted dictionaries mean. So instead of organizing the data as we saw on the left-hand side, what we have is we have the hash table is just these indices. So for each element, we store an index into another table, into an array that stores these tuples. And these tuples we simply store in the order in which they are inserted. So in this way, if I look up in the hash table, I get this index, I can look into that other table. And that other table is the one that is sorted. So the hash table is simply still a hash table, but this is now much more compact than the version on the left-hand side. And that's what sorted dictionaries are about. Let's also wrap up this part about hash tables in Python. Dictionaries are implemented using hash tables, and collisions are resolved using open addressing. If you have a too high load factor, or if you have too many deletions, the table is simply rebuilt. You have this very interesting hash function, and to get compact hash tables, the data is separated from the hash table, which only stores indices. That's all for today. See you next time.